All right, welcome back. So last time we dug into the whole idea of backtracking, right? This strategy of, well, trying something, hitting a dead end, and then smartly backing up to try another path. Today, we're going to put that theory into practice with a classic problem. I mean, this is a real rite of passage for almost every programmer out there. We're talking about the n-queens problem. So let's start with the puzzle itself. What exactly are we trying to solve here? The rules, they're actually pretty simple. But don't let that fool you. If you don't have a good strategy, this thing is a serious brain teaser. Okay, so here's the big question. Can you take n queens and place them on an n by n chessboard so that no two queens are threatening each other? Think about a regular 8 by 8 board. That means you've got to place 8 queens where every single one is safe from all the others. It's a puzzle of pure placement and constraints. And to solve it, you really have to understand the queen's power. She's the heavy hitter in chess, and her moves define the rules of our puzzle. Basically, any square that's in the same row, same column, or on the same diagonal as a queen, well, it's a no-go zone. It's off limits. Yeah, so think about it. Every time you put a queen down on the board, you're instantly blocking off a bunch of squares, all the way across horizontally, up and down vertically, and in both diagonal directions. It's like you're casting this huge shadow of attack vectors. And this is where the scale of the problem just gets wild. You might be thinking, okay, how hard could this really be? Well, for a standard 8 by 8 board, there are over 4 billion possible ways to place those 8 queens. Billion with a B. Just trying to check every single one of those, you'd be here forever. That's what we call a computational explosion. And it's why a simple brute force approach just won't work. It's a total non-starter. Okay, so why do computer science students and engineers spend so much time on this one chess puzzle? Well, the secret is, it's not really about the chessboard at all. It's actually a perfect little model for a whole class of problems we face every day. See, when you're solving the n-queens problem, you're not just playing a game. You're practicing the core skills of algorithmic thinking. You're learning how to enforce constraints, how to be efficient by reducing the search space, how to structure your code, and really how to reason about a problem systematically. It takes these big, abstract ideas, like pruning a search tree, and makes them tangible, something you can actually see. All right, so if brute force is out, if trying everything is a terrible idea, what's the smarter way to search? Well, if you remember our last session, you've probably already guessed the answer. This is a perfect job for backtracking. And this really shows the night and day difference. The brute force way is just chaos. You throw all the queens on the board randomly and then check if it worked. Total waste of time. Backtracking, though, it's methodical. It places just one queen at a time, row by row. After each placement, it stops and asks, is this okay? Are we still following the rules? If yes, it moves on. But the second it hits an invalid spot, it immediately abandons that path. It doesn't waste another second on a failing solution. Now, there's a really simple but powerful insight we use here. We decide to place queens only one per row. By just making that our rule, we've instantly solved one of the constraints. We can't have 2 queens in the same row. So our algorithm only needs to check 2 things at every step. Is this column already taken? And are the diagonals safe? That's it. If the answers are yes, we proceed. If no, we backtrack. So let's just imagine how this unfolds. The algorithm places a queen in the first row. Looks good. It moves to the second row and finds a safe column. Great. Then the third row finds another safe spot. But then it gets to the fourth row and it realizes, wait a minute, there are no valid columns left. Every single one is under attack. Now, this is the key moment. Instead of quitting, it backtracks. It goes back to the third row, picks up that queen, and moves it to the next available safe spot. And then it tries to move forward again from there. It's this constant dance of place, check, backtrack, repeat. Okay, that process works. It will find a solution. But a great engineer always asks, can we do better? Can we make it faster? And the answer is yes. There's a brilliant optimization insight we can apply here. Here's the thing. When we're checking if a new spot is safe, do we really need to look at every other queen on the board again and again? That feels inefficient. What if instead we just kept track? We can use simple arrays or sets to remember which columns are used, which diagonals are used, and which anti-diagonals are used. It's like we're just flagging the danger zone. And this is the trick that takes the algorithm from good to great. Suddenly, checking for safety isn't a slow scan of the board, it's a super fast lookup. We just ask, is this column in our used set? Is this diagonal in our used set? It's an instant check. This simple change turns a potentially slow operation into a constant time one, and that is a huge performance win. Okay, so let's zoom out. We've solved this one specific puzzle, but what's the big picture? What's the principle we can take from this puzzle and apply to, well, everything else? What the N-Queens problem really teaches us is fundamental. It shows how backtracking is a powerful way to enforce correctness step by step. It shows how pruning, that idea of cutting off bad branches early, is what saves us from a computational nightmare. It shows us how a few simple constraints can elegantly guide a very complex search. And maybe most importantly, it proves that the structure of your algorithm often matters way more than raw processing speed. And believe me, this is not just an academic exercise. These exact same principles are at work in systems you use every day. Think about a scheduling app trying to find a meeting time for 10 people. That's a constraint problem. Or a system allocating resources in a data center. Or even a tool that generates test cases for new software. They all use the same core logic. Explore the possibilities, but backtrack the moment a constraint is violated. So it's really important to see that the chessboard here, it's just a teaching surface. It's a visual aid. The real lesson is the mental model it gives you for solving a huge range of complex problems. You know, by truly understanding this one problem, you've really leveled up your algorithmic maturity. You can now look at a problem and recognize, hey, this looks like a job for backtracking. You know how to think about designing the right constraints, how to keep your states small and efficient, and how to reason about why your approach is a good one. This is a massive step forward. But here's the thing, backtracking isn't a silver bullet. It's not the right tool for every job. What happens when your algorithm keeps solving the exact same subproblem over and over again? That sounds wasteful, doesn't it? Well, for that kind of problem, we need a different strategy. And that's what's next. We're going to talk about dynamic programming and when and why we make that strategic shift. So let's leave it with this final thought. The biggest lesson from the N-Queens problem and from algorithm design in general is this. Great algorithms don't try everything. They know what not to try.